Today I'm going to be talking about a particular aspect of AI, a critical aspect of AI, and that is the underlying compute infrastructure. What I want to do is actually paint an arc of history, actually, in terms of where computing has been over the past 50 years and where that's going to lead us over the coming 5 or 10 years. It's really actually, for me, the most exciting time in computing. I've been at this now for some time, and the trends are really just astonishing. So I want to share some of those with you. Okay, so for me, the most exciting thing about this moment is that we are transitioning from what I'll refer to here as the age of information to the age of insight. Okay? So what we've done over the past 25 years or so, and it really is stunning if you think about it, is we've made it such that the totality of human knowledge is available at your fingertips, anytime, any place. Like 25 years ago, in the year 2000, that would have been science fiction. Today, you can pull out your cell phone and access virtually any fact, virtually any video, virtually any book, virtually any song, instantaneously. Really, really stunning. However, we're now in a place where actually the totality of human information is somewhat overwhelming. What we're transitioning to is needing insight. How do we actually act on the information? How do we get the information that we need for us in that moment, quickly, helpfully, but also personally? And this is going to be a major challenge that's going to once again reshape computing. So for me, let's start with history, actually. And I'm a fan of history, student of history on multiple levels. So I study computer science history a little bit as well. You could start arbitrarily back in terms of the history of computing. It goes as far back as humanity itself, actually. But I'm going to start around 1970. 1970 was actually really an incredible time. The basis for modern computing, let's say SQL, time-shared computers, UNIX, C, right around then object-oriented programming, Ethernet, the mouse, the graphical user interface. So much of what we actually take for granted today was invented in 1970, plus or minus 4 years. So really an astounding time. What we've seen is just unbelievable progress over the intervening decades, actually. So when I got my first internet account in 1988, there were 50,000 total people on the internet. It's a medium-sized city worth of people across the planet. Just the astonishing exponential growth over epochs. I could spend an entire talk going over these epochs, but we've made a shift from a small number of computers connected across the planet, mostly for supercomputing, to the invention of distributed computing, remote procedure calls, and really basically having local area networks that businesses could operate on. From there, HTTP was invented. I really started my career right around the same time when something called NCSA Mosaic came out. Right, the first graphical user interface, web browser, 1993. And again, astonishing takeoff from there. This last epoch, the fourth epoch that I refer to here as web search and planet-scale services, really was another major, major shift. In other words, we went from a place where software was delivered across the planet as a service. Many of you might remember there was a time when if you wanted to buy software, you went and you bought a box, and it was shrink-wrapped, and you unwrapped it, and you pulled out some media. Right? No one does that. Like, who does that? In the year 2000, everybody did that. Right? We made a major transition delivering software as a service, information as a service across the planet. And that set the stage for this new fifth epoch of computing, which is really actually all about data, all about artificial intelligence and machine learning. Right? It's now data-centric computing. The fact that we had access to the totality of human knowledge and just massive amounts of compute has made it possible for us to take on new opportunities. Okay, so for sure the work that has happened over the past 25 years or so has been absolutely transformative. Now going from 50,000 people on the internet in 1988 to 2, 3, 4 billion actually, right, and growing. Interesting thing is that the computing infrastructure has transformed with it. And so what I'll tell you about very briefly here is that the way that we build infrastructure today in the internet era is radically different than the previous era. What you see here are some pictures of entire buildings, warehouses. First they were 10 megawatts, for Google's first data center in about 2002, 2003. Then 40 megawatts, 100 megawatts, and beyond. Lots of people are doing this. We now have warehouses, enormous buildings, filled with row after row after row of commodity network, storage, and compute. Essentially off-the-shelf components that you or anybody could buy, but organized in a particular way at massive scale. This was not how computing was done right around 2000. When you ran out of compute power in the year 2000, you went and you bought a bigger computer. When you ran out of storage in the year 2000, you went and bought a bigger storage array. You scaled up. You threw away your old one, you went to the new one. Now we scale out. We build more and more in an array of commodity parts. This actually completely transformed software as well. So in other words, I have examples from Google, same things happened at lots of companies. We went from a place where we didn't have a single storage system that ran on a single computer. We had the Google File System, GFS, that essentially took, at the time when it was first introduced back in 2002, 20,000 disks and gave you the illusion, and this was across 10,000 servers, gave you the illusion that you had one file system. Right? And that was fairly shocking. It was considered actually a bad idea at the time. Why would you build a system that way? And it turned out to actually take off. MapReduce, the notion that you could actually run analytics with a single piece of code and distribute it across the same 10,000 servers, taking advantage of your storage array. Moving beyond SQL to Bigtable, treating an entire cluster as if it were one computer that you could submit jobs to, on and on. Right? And then one of the most interesting ones, TensorFlow, launched in 2016, now almost 10 years ago, that really laid the foundation for distributed training for machine learning models. Initially, running on CPUs, those same CPUs, tens of thousands of them, that were spread across the data center. Taken together, over about a 20-year period, from 2000 to 2020, the community as a whole delivered a factor of 1,000 performance efficiency improvements. Right, let me just pause for a second, because for me, that's really stunning. For the same money, you could get 1,000 times the capacity, whether it's networking, storage, or compute. When you talk about 3 orders of magnitude, you start to take things that used to be considered impossible and imagine new ways of doing things. And that really was what this scale-out revolution was about. Many design principles that drove this transformation. For time, I won't go through them in detail, but essentially we had to rethink how everything was organized. One of the key tenets that I'll spend a minute on was loosely coupled software. And what this meant was, even though you were running on 1,000, 10,000, perhaps 50,000 servers, the failure of any individual element should be tolerated as just a fact of life. So in other words, here at Google, if we lose a server, you don't notice that your web search results didn't return the correct values. In fact, if we lose a whole rack, you don't notice. We actually don't take it as an emergency, even if we lose a whole rack. We could lose a whole cluster, an entire building. We would notice that, you wouldn't. Right? And that's how the software is structured. And this was a radical departure from how software used to be structured. Things have really exploded. So what I will say, and again, some really interesting trends over the past 5 or 10 years, but what enabled us to get to this point was the continuation, the ever continuation of Moore's law. In other words, what was happening up until about 10 years ago was you got double the transistors on a package of silicon for the same cost and the same power. Actually, starting more than 10 years ago, those trends started to slow and stop. Today, amazingly, 60 years after Moore's law was first articulated, you're still getting double the number of transistors every 2 years or so per package, but now for double the cost and double the power. Super impressive still, but less exciting. Yes, you get more power, but you have to pay for it, compute power. Yes, you get more compute power, but you have to now provision the watts for it as well. So this meant that we had to rethink how we go about scaling out our compute infrastructure at the exact same moment when the demand for computing had never been larger. I've never seen anything like this. So this shows from 2017, when transformers were first invented here at Google, to today, the growth in compute requirements to train our largest models, right? From the first transformer to BERT for language translation, all the way up to Gemini 2.5 Pro, Flash, and more. Year over year, 10x compute demand per generation. And again, this is indicative of what's happening across the field. So just as the underlying trends in terms of the capability of the underlying hardware slowed and stopped, the demand for computing exploded. Okay, so that says that we actually need to get the next 1000x way faster than we did before. Right? We delivered 1000x over 20 years in the last epoch. We have to do 1000x ideally in 3 years now to keep up with the demand for compute, right? 10x is where we're at. This is what it's going to take to go from the age of information to the age of insight, where we can be delivering across the planet to billions of users, both business, home, personal, the insights that they need in the moments that they need it. It really is a renaissance, right? In other words, why I find it so exciting is that we had, over the past 20 years, come to a place where there was accepted conventional wisdom. When there was a problem, people immediately knew what the solution was because they developed the patterns. Now, what's exciting for me is all the conventional wisdom that I had developed over the past 20 years, more often than not is wrong. Okay, so you could think, well, we're happy about being wrong. Yes, in fact, I am, because that means I get to learn a lot. We get to learn a lot. The things that we did no longer work. We have to actually, and that means that we're going to need a renaissance across so many different areas, from microarchitectural advancement all the way to the models that underlie machine learning. Okay, so what I can guarantee at this point, it's an easy prediction, is this next revolution that we're in the early to middle stages of is going to render the current compute infrastructure unrecognizable. And lots of fundamental shifts. We've talked about some of them. Again, I won't have time to go through them in detail, but the nature of GenAI computation is first and foremost. We went from a time where you actually could take your arbitrary software, wait 2 years, buy the latest server, and it got twice as fast without you having to do anything. And that happened for all of your computation. It was magic. Now we're in a place right now where actually an increasing fraction of our computation is very specialized of a particular type. And that shifts the entire equation in terms of how we build things. The other two things I'll call out here, we'll go into a little bit more detail later, is reliability. We're at a place right now where the failure of a single accelerator is actually a problem. I told you how we wouldn't notice if a server went down today. We do notice if a single accelerator goes down today. If a whole rack goes down, major problem. Power and sustainability. We're going from to a place where actually power will likely be the limiting factor for the kind of work that we want to do moving forward. And how you design your infrastructure, where your power is the primary constraint, means that actually you go about the design very differently. Okay, so we've been at this actually at Google through some combination of good fortune and foresight for actually a decade plus. Our first TPU, tensor processing unit, actually started its design work in 2013, 12 years ago now, and launched into production in 2015. This was well before chat, GenAI, or anything like that. It was driven by a simple observation, that if our users at Google wanted to interact with Google via voice for, let's say, 30 seconds a day, this was back in 2013, we would have to build 2 more Googles to support just that one use case. Right? So just voice recognition was so expensive from a computation perspective that it was unimaginable for us to actually support it. And even in 2013, we were very fortunate, had a lot of resources, could imagine building a lot of infrastructure. But building that much infrastructure for one use case seemed impossible. Now, the good news was the computation required was very regular. It involved a large number of matrix multiplications, enormous matrix multiplications, in fact, as the basis for that computation. And we realized that actually we could do it 100 times more effectively by building custom hardware to solve this one problem. Now, interestingly, remember the golden age of Moore's law. This was so counter to all conventional wisdom. You did not build specialized hardware. General purpose CPUs always won because they advanced so rapidly. But this one use case was so specialized, and the uplift, 100x, was so large, and the benefit so large, we decided to go after it. Even at Google, this was a somewhat controversial decision because everyone had developed the same conventional wisdom. You never build specialized hardware for a specialized domain. You're going to lose in the end. TPUs were deployed. We built the custom hardware super fast. Got it into production. And actually, it was a hit across the data centers. Did support the voice recognition. We quickly realized that by stitching these together in a small cluster, we could not just do voice recognition, we could efficiently do the training for the same models and support advanced use cases like translation from language to language. And that led to TPU v2. From there, v3, all the way out to our announcement this year for our 7th generation Ironwood. And at this point, we went from single TPUs 10 years ago doing voice recognition to an ensemble of 9,000 chips really operating at many megawatts, coordinated on individual problems at nanosecond granularity. And the models have really become incredible. So we've gone from dense models of enormous size to sparse models, where we have many experts, and we only activate portions of the model in response to individual queries. Now, I show this picture because the training and even the serving for these models takes place on the training side. Think of it as tens of thousands of TPUs. Serving side, hundreds or more of TPUs. These models, trillions of parameters. They're way bigger than can fit on even the biggest TPU or the biggest GPU, pick your favorite accelerator. The communication and computation across all these individual elements has to be partitioned across these tens of thousands of elements. So the hardware for networking, the hardware for memory to store all the activations, the parameters and more, and all the computation has to be intricately spread across the hardware. We're in a place right now where we're not only just designing custom hardware, we're co-designing it with the researchers. And this has been one of our really exciting benefits here at Google, where we get to work shoulder to shoulder, side by side with the leading researchers that since the beginning, actually, Transformers and even before, have been developing the leading models. This allows us to develop the hardware, looking forward to what will be needed for the models. Okay, so we've essentially broken all the rules, all the conventional wisdom that has been developed over the previous, let's say, 20 years in designing TPUs. So again, conventional wisdom for the first, let's say, 50 years since 1970 was whatever networking problem you had, you would solve it with Ethernet. And if you chose something else, you were making a mistake. For the first time, we've actually built a custom network interconnect, actually with the networking integrated with the TPUs directly. So there's no switching. That supports one use case and one use case only, which is parameter distribution from one TPU to the other at nanosecond granularity. Now, my own academic background is in networking, and I remember when I saw this idea from the TPU team at the time, I said, oh my gosh, this is a mistake. You only go with Ethernet, don't you know? And I was wrong. I was so wrong, and I love it, actually, that I was so wrong. An example of where it breaks, and actually the custom design, in this case is called ICI, network, is the exact right way to support this use case. We went to liquid cooling. Right? For, again, decades, conventional wisdom said, you only do air cooling. And we were actually the first, a decade ahead of anywhere else to go with liquid cooling. We built an optical circuit switch to support the reliability and reconfiguration needs of the computation. So in other words, we actually leveraged MEMS mirrors to allow for communication to take place entirely in the optical domain with no electrical processing taking place when moving between TPUs. And this turned out to be critical for the reliability of the system. We moved away from IEEE formats for floating point. We actually, again, broke conventional wisdom and said we're going to make a representation of data, floating point data, that is only good for training. Didn't seem to make a lot of sense at the time, but has been actually many integer factor improvement in performance. We went from commodity DRAM to HBM, co-packaged with the compute for the highest bandwidth memory. And we actually, of course, delivered very specialized hardware for scatter, gather, and sparse operations. Taken together, what this means is that we have at least a factor of 100 if not more, for a given computation, ML computation, training or serving, relative to what you could do on a general purpose CPU. Right? And that's what makes it worth it generation over generation. Okay, and this is just part of an AI hypercomputer stack. So the hardware is impressive. Again, an ensemble of 140 plus racks, 9,000 chips, specialized network, optical circuit switching, and more.
I'm not going to put this in the recording, but you've been so profound. Can I hear one person just say an aha from Amin that you've heard so far? Who wants to do it? Someone. Something profound. No, like what did you learn in this? There's someone. Okay. Someone else. Someone else. Okay. So sorry, you're doing good. I just want you to get that positive feedback.
Thank you for that. It is okay to be wrong, and fortunately for me, I've been really good at being really wrong a lot in my career. I think the key is, if I may give a small personal piece of advice, is to realize when you're wrong quickly as well. If you're going to be wrong a lot, you have to figure it out quickly. Anyway, back to the AI hypercomputer. So the hardware is super important, but what we found is actually that it's the entire software stack, all the way up to the model, that's most important. So for us, actually, a real key differentiator, when you saw those pictures of communication across parameters and weights and everything else going across the models, reliability is absolutely key, because essentially for every step of the computation, every TPU has to coordinate with every other TPU. One failure at the scale of tens of thousands, and actually the computation stops, because the error can propagate, and actually your whole answer could very quickly wind up being wrong. So the other thing to note is that we, and actually the whole community, are building chips at the bleeding edge of what's possible. Like in every generation, what is the biggest, most powerful chip we can build? That means that the reliability is also at its bleeding edge as well. We've had to develop very advanced techniques to actually detect failures and recover from them very, very quickly. Because if you just do the math, if you imagine, let's use round numbers, 100,000 TPUs coordinating on a computation, any one of them fails, the whole computation stops. Now, these computations run for a long time. You can see how you can easily spend more of your time detecting and recovering from a failure and restarting than actually running the job. And we've been there, believe me. So we've spent a huge amount of our effort actually in putting in hardware support, software support, telemetry, and processes to make sure that the computation always is running. And one of the things that probably we're most proud of, we've got amazing hardware, but we can achieve good puts well over 90%. What that means is that despite the failures, and they do happen, we're able to catch them, reconfigure, and keep running such that we lose no more than, say, 10% of total capacity. That at scale. And as we've continued to scale it out, we're able to maintain that. If I had more time, I could show you the math for where you would see just how impressive that would be to maintain a good put of 90% at this scale. Okay. Also, I think it's really important. I talk about TPUs because we have a lot of experience with them. I have a lot of experience with them. Many of the same things would apply to NVIDIA GPUs. Really astounding pieces of hardware, really astounding connectivity on the network side, and really an enabler for this GenAI revolution that we're seeing. We're proud, actually, to be a key partner to NVIDIA, and we typically are actually first to market with each of their products. This is highlighting some of the latest, the B200s, and more that we've actually launched on Google Cloud as well. Briefly, because actually delivering GenAI to the planet, delivering insights to the planet requires other elements for this AI hypercomputer, and that is the network. We've been fortunate, actually, at Google really to be driven by YouTube, which is one of the most network-intensive services in the internet. And so we've been privileged to actually have them driving our requirements. Now with GenAI, we're happy to say that we've got actually a global network with 42 regions, 127 zones. We have probably the largest edge presence among all the hyperscalers, and probably the largest number of subsea cables connecting all the continents together, right? 2 million plus miles of lit fiber across the planet. Right? And so this all comes together in our Cloud WAN that connects all these services together across the planet. I've talked about this a fair bit in terms of reliability. These ML workloads require high reliability, and these ML supercomputers really pose unique challenges that go counter to all the conventional wisdom that we developed for web search and more. And we're constantly staying at the edge of what's possible, which means that actually the techniques we develop for the reliability are as important as raw performance. And so just to show this pictorially, we talked about the sum. If you don't account for reliability, when you say, hey, how many flops does my chip have? How many floating point operations does it support? How much HBM does it have? You might draw this dashed blue line of how fast your computation can run. In practice, likely it will be an integer factor worse, right? Because you can't multiply flops by number of chips. You can't multiply high bandwidth memory by number of chips to figure out how well you will run in practice. Actually, you'll likely do much, much worse if you just deploy in the straightforward manner. Serving, one of the things that we're actually most proud of over the past year is the dramatic improvements in our serving efficiency. This means actually some really advanced software techniques. So we've published actually recently some of our carbon efficiency work that has been driven by factors of 30 and 40 improvements in serving efficiency. Some of it from hardware, but actually most of it from software. So here's an interesting technique that we've also published on called speculative decoding. The key idea here is that actually many of the tokens that you see generated, next words that you see generated in GenAI, are very easy to predict. Some of them are really hard, but many of them, like, okay, the next word is going to be the. Probably it's really easy to predict that. You can use a small model to do so. You don't need your largest model to do it. What we found is that we can have our small model running ahead of our large model, predicting an ensemble of tokens, words, and then verify it with our large models running behind. And again, integer factor, 10x or more. The nice thing here is that this is a fantastic idea coming out of our research teams, but there's lots of these from us and others, to be clear. I'm giving you one example from Google because I know it. But the point here is that actually there's a lot of low-hanging fruit in optimization that we're going to see driven sort of year over year. It's early days, and that also makes it exciting. Okay, I talked about power a bit. The main message I want to give here as I run out of time in just a second is that we're going to have to transition from a world where we think about performance per dollar to performance per watt. And this is a transition that we've made here at Google. In other words, when we evaluate architectures, we look at what the delivered performance is per watt of provision power. And this has been an eye-opener and has broken a lot of conventional wisdom for us as well in terms of how we would do things. One interesting thing here is that you can get away with provisioning a lot more power if you're willing to live with lower reliability. One recent third-party study from Duke Energy actually says that you can get 100 gigawatts of extra capacity in the US. That's a lot, by the way, 100 gigawatts. If you're willing to support 1% load curtailment. What that means is if you're willing to have 3.65 days a year where you don't take any power, a huge amount of power gets unlocked. Now, consider machine learning training. 1% of the time, you can actually stop. Serving, perhaps not, but training, yes. How would you manage a world where actually you have to shut down your computation for possibly hours, days, in some cases, over the course of a year? Okay, so I'll skip some of the very cool optimizations. I'll also skip over, actually, probably one of the most important topics here is the security side and the privacy side. And I'll go to the conclusions. I think what you've hopefully seen is that actually we've driven transformation across all of industry in this last epoch of computing. And we're going to deliver equal or more, and I think a lot more in this epoch. This is going to enable us to transition from delivering data to the planet to delivering insights. And that, I think, is going to be a real uplift for so many of us. We didn't even talk about the many, many use cases. To do so, we have to actually discard all of our conventional wisdom. Right? The tools are all there, but we have to learn how to put them together in really interesting and new ways. Thank you very much.